This is SpaceTime Series 27, Episode 151, for broadcast on the 16th of December 2024. Coming up on SpaceTime, a new view of one of the solar system's biggest craters, new gravitational wave maps revealing hidden black holes and cosmic structure, and NASA conducts the first ever aircraft accident investigation on another planet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New observations of the moon's south pole have shown that the giant Aitken Basin crater is far more circular than previously thought. The South Pole Aitken Basin is the moon's oldest and largest visible crater, a massive geological scar 4.3 billion years old, which preserves secrets about early lunar history. The immense impact crater on the far side of the moon is roughly 2,500 kilometres in diameter and between 6.2 and 8.2 kilometres deep. This is one of the largest known impact structures in the solar system. Previously, based on some features of the basin, scientists thought the crater was probably shaped more like an oval or ellipse. And for years, scientists believed that this enormous crater was formed by an object striking the moon at a shallow angle, possibly as extreme as a rock skipping across the surface of water. Now, under this hypothesis, very little debris from the impact would have been spread across the lunar south pole. And that's important because that's going to be the primary landing site for both the upcoming Artemis missions by NASA and ESA and also the future joint Russian and Chinese moon missions. And that's where this new study comes in. Astronomers are suggesting that, based on their new information, the impact may have been much more direct than previously thought, resulting in a much rounder crater. A report in the journal Earth and Planetary Science Letters claims this new finding challenges the current understanding of the moon's history, with significant implications for NASA's future missions to the lunar South Pole. The study's lead author Haynes Bernhardt from the University of Maryland says studying the South Pole Aitken Basin is holistically challenging due to its sheer enormousness, which is why scientists are still trying to learn its exact shape and size. In addition, some 4.3 billion years have now passed since the basin was originally formed, and many other impacts in the same area have obscured its original appearance. The new research challenges many existing ideas about how the massive impact occurred and distributed material, but it has placed astronomers a step closer to a better understanding of the moon's early history and its evolution over time. Using high-resolution data from NASA's Lunar Reconnaissance Orbiter, Bernhardt and colleagues developed an innovative approach to understanding the South Pole Aitken Basin's complex structure. They identified and analysed over 200 mountain formations scattered around the basin, geologic features that the authors suspected could have been ancient remnants of that original impact. From the distribution and shapes of these mountain-like features, the authors realised that the impact should have created a far more circular crater from which significant chunks of planet-forming material would have been dispersed across the lunar surface, including a decent scattering in the South Pole region. Bernhardt says a rounder, more circular shape indicates that an object struck the moon at a more vertical angle, similar to dropping a rock straight down onto the ground. This circular impact implies that ejected debris from the impact would have been more evenly distributed around the ground than originally thought, which means that Artemis astronauts or robotic missions to the south pole of the moon would be able to closely study rocks that may have originated deep within the moon's mantle or crust, material that's typically impossible to gain access to without a lot of digging. Instead, the impact event provided that. Now, what all this means is that these lunar rocks could provide crucial insights into the moon's chemical composition, and they could help validate theories about how the moon may have been created from a massive collision between the early proto-Earth and a Mars-sized planet dubbed Theia some 4.5 billion years ago. Recently, India's Chandrayaan-3 lunar rover detected minerals indicative of impact debris coming from the lunar mantle close to the moon's south pole. And that supports the author's new hypothesis. Bernhardt believes that his team's research provides crucial information for future moon missions, helping mission planners and astronauts identify areas to explore and what minerals they may well encounter there. You see, a thick layer rich in material from the lower crust and upper mantle could offer unprecedented access to the moon's complex geological history, potentially shedding light not just on the moon's formation, but also the transformative events that help shape our solar system. This is SpaceTime. Still to come, a revolutionary new gravitational wave map which is revealing hidden black holes and cosmic structure, and NASA conducts the first ever aircraft accident investigation on another planet. All that and more still to come on SpaceTime. Astronomers have created the most detailed maps ever of gravitational waves across the universe. But this new data are based on pulsars rather than gravitational wave interferometers such as LIGO and Virgo. This stunningly new view of the cosmos, reported in the monthly notices of the Royal Astronomical Society, was achieved using minuscule nanosecond changes in the timing of pulsar beams emitted by rapidly spinning neutron stars to determine when a passing gravitational wave affected the fabric of space-time surrounding the beam. The result has produced the largest ever galactic-scale gravitational wave detector, discovering a background of gravitational waves right across the universe. One of the study's lead authors, Matt Miles from Swinburne University in Osgrav, says this research opens new pathways for helping scientists understand the universe we live in. You see, studying this newly seen background allows astronomers to tune into the echoes of cosmic events across billions of years. Miles says it reveals how galaxies, and the universe itself for that matter, has evolved over time. The study used data collected by South Africa's Meerkat radio telescope array to examine mergers between supermassive black holes and how they shape the universe we see today and its cosmic architecture. The studies uncovered further evidence of gravitational wave signals originating from merging supermassive black holes, capturing a signal much stronger than similar global experiments, and in just a third of the time. Miles says it hints at a far more dynamic and active universe than what scientists had anticipated. Using the pulsar timing array, Miles and colleagues constructed a highly detailed gravitational wave map. And this has revealed an intriguing anomaly, an unexpected hotspot in the signal, suggesting a possible directional bias. You see, the presence of a hotspot could suggest a distinct gravitational wave source, such as a pair of supermassive black holes billions of times the mass of our Sun. Looking at the layout and patterns of these gravitational waves shows how the universe exists today, but also contains signals from as far back as the Big Bang 13.8 billion years ago. The authors say there's more work to be done to determine the significance of the newly discovered hotspot, but it is an exciting step forward. The new findings are raising questions about the formation of supermassive black holes and the early history of the universe. And further monitoring with Meerkat will refine these gravitational wave maps, potentially uncovering new cosmic phenomena. Miles says the research will also help astronomers exploring the origins and evolution of supermassive black holes, the formation of galactic structure, and the underlying cosmic structure.
When we think about something like LIGO and Virgo and those black holes colliding, we're talking about black holes that, while still incredibly massive, are on the order of the mass of our Sun. So they're going to be around 10 times the mass of our Sun, maybe 200 times the mass of our Sun. But what we're looking at are the ones that sit at the centers of galaxies. So there's things called supermassive black holes, and they're about 10 billion to 100 billion times the mass of the Sun. And so we don't even really get to see the actual collision. What we're seeing is them distorting space and time as they even just come near each other. As galaxies tend to merge and they hit each other, these black holes will sink to the center of that merged galaxy, and they'll start to in-spiral towards each other. And they'll start to change how space and time interact, and they'll send out these gravitational waves, these ripples in space and time, just in that phase where they're just coming close to each other.
And is that still being measured by an interferometer, a gravitational wave interferometer, or is it being measured by something different?
It's a little bit different. So what we're measuring it by using this thing called a pulsar timing array, which is, I'll just quickly explain what pulsars are. They're neutron stars. So they're basically remnants of dead stars. After stars explode, they'll either turn into black holes at the cause, they'll have this incredibly dense singularity, which we call a black hole, or they'll turn into a neutron star, which is effectively just a star really just made of neutron sort of degenerate matter that's just being sort of kept alive by the pressure that's there. And the only difference between a neutron star and a pulsar is that as the neutron star spins around, if its magnetic axis aligns with the Earth, we get this sort of lighthouse beam of radio waves that hit us. And so we get a pulse of radiation. And so we call it a pulsar because of that.
This is what we see in things like the Crab Nebula and that.
Yeah, absolutely. There's a pulsar in the Crab Nebula. And yeah, so what we try to do is we look at a lot of pulsars at the same time. Like we observe them quite regularly over some period of years. And we basically just try to predict when that pulse from the pulsar is going to come next. But these things are really predictable because they're so dense, it's really hard for them to sort of change the rate at which they spin because they've got so much momentum in them.
And although they move over cosmic time, on the human time scale, they're pretty stable. They stay where they are in space, and we can use them as cosmic marker posts almost as to point to different directions, different positions in the cosmos.
Yeah, absolutely. 100% right. Yeah, over a human lifetime, we don't really see any discernible true movement. And so we always have a very good idea of where they are. So as we go and we try to observe these things very regularly and try to predict when the pulse from the pulsar is going to hit the Earth, what we can sort of ascertain from that is if we're wrong about when the pulse is coming from the pulsar for a lot of pulsars at the same time. So we observe 83. And if we're wrong about when the pulse is coming from all 83 in a very specific way, then we can say that we've observed a gravitational wave passing through. So there's basically what's happened in effect is the space is sort of stretched or compressed in between us and the pulsars as the gravitational wave is coming through and passing through Earth.
So the pulsars are doing the same thing as the gravitational wave interferometer in, say, LIGO or Virgo would be doing.
Yeah, very similar things. But rather than looking at sort of the diffraction pattern that you get from the interferometer that gives you the indication of a gravitational wave, instead we're looking at about changes in tens of nanoseconds from when we thought the pulse from the pulsar was going to arrive at the Earth. And so that's really the primary difference. The other difference is that we're not really looking for individual gravitational waves. We're kind of looking for every gravitational wave that's happened over sort of cosmic history. So we sort of describe it as this gravitational wave background. It's more sort of like an ocean of gravitational waves that are always passing through and interacting with both the Earth and the pulsars. And so we can measure that in the same way that you can sort of measure how active a lake is and how active the waves on a lake is. You know, the boat, if you imagine the boat is the Earth, the boat's sort of rocking around in that lake. If you've got little buoys all around the lake, which you can imagine as the pulsars, they're also going to kind of be rocking. And so we're trying to measure that rockiness and how much the Earth is sort of surfing on the waves on that lake surface.
And you're able to use that to roughly determine where these major cosmic collisions between supermassive black holes have been taking place.
Yeah, well, that's one of the most exciting things we kind of found. So we're still sort of a work in progress. We don't have the evidence. We've sort of got our first show at how we can do this. We don't have evidence to definitively say anything exactly, but what does certainly look like there is more gravitational wave strain energy in certain parts of the sky than there is others. And this sort of implies that there's this anisotropic spread of how these gravitational wave sources are distributed over the sky. There's still a chance this could be a bit of a statistical anomaly, but it is sort of a very exciting first step into a new way to discern this gravitational wave background.
When you look at where this anomaly is or where these anomalies are, do they line up with anything like particularly large clusters of galaxies or anything like that?
So from what we've had a look at so far, we can't really definitively say, and there's a bit of sort of ongoing work to see if this in fact is happening, if it does line up with a particularly large galactic cluster. But the hotspot that we found, this like little strong point of the sky, is still quite large. So it's a large area of the sky. So to localize it down to a particular galaxy or a cluster of galaxies may still actually be quite difficult. So that
you can't say it's Laniakea or the Great Attractor or anything like that.
No, I don't think we can say anything just like that just yet, but people are on their way to start to do targeted searches, which is to look in areas on the sky that we do seem to find these hotspots of gravitational wave power and see if they line up with any galaxies there or any other sort of clusters or anything that might emit a large amount of gravitational waves on the scale at least.
And key to this has been the use of the South African counterpart to the Square Kilometre Array Pathfinder.
Meerkat. The Meerkat radio telescope has been just exceptional. In my very biased opinion, I would say the Meerkat radio telescope is probably the best radio telescope that's around at the moment. It's one of two very, very good, what we would say, next-generation radio telescopes. So the other is the 500-meter aperture square telescope, which is in China. But these are two incredibly sophisticated telescopes which allow us to observe pulsars with incredible sensitivity. So it really allows us to measure the signals that are coming from these stars far more precisely than we're able to with another telescope. For example, the Parkes Radio Telescope in New South Wales, if they were to look at one of the pulsars for about an hour, we would get the same sensitivity and data quality out of that pulsar if we were to look at it for about 5 minutes. So it's just such a sensitive machine. And what that really means is that we can look at a lot more pulsars than other collaborations are able to. And we're able to predict when their pulses should come in with a far greater measure of accuracy and precision, which really helps this sort of background measurement be possible within only 5 years, where it's taken other collaborations almost 2 decades.
And what's this telling you about the universe?
What it tells us about the universe, really, it's interesting in the sense that we are finding this background in the way that we are. Every collaboration in the world so far that's looked for it, even though it's taken them a little bit longer than it took us, has found some indication of a common signal that seems similar to a gravitational wave background, that we all think is likely to be a gravitational wave background. What's sort of interesting is that what we're seeing in sort of latest look at it is that the amplitude or the signal power that we're observing is a little bit larger than the other collaborations have seen. And this is something that's really quite interesting because we don't expect this signal to change over many years. Our work has happened a couple of years after the other collaboration, and it really should take something like millions of years for this signal to change. And so we're sort of now entertaining the idea that this gravitational wave background signal might be something that isn't quite stationary, that might be able to change on shorter timescales. And so physicists around the world at the moment are trying to create explanations as to why this could be. And some people more recently have come up with some very interesting explanations that if you had sort of a more chaotic in-spiral of these supermassive black holes where they were, rather than circular, very elliptical, you would get perhaps a signal that could change on very short timescales. And so it's really making us sort of reconsider what we think is going on. And more than that, it's giving us an idea of how many of these massive galaxy mergers might have occurred through our cosmic history so far. Although I can't quite quote you on that number. There's a lot of debate on that.
Do we still need projects like LISA with this sort of timing array?
Yeah, absolutely. LISA's going to be just an exceptional instrument, and I think everyone in the community is incredibly excited when it comes up. The difference between what we can see and what LISA can see is pretty simple, but they complement each other just so beautifully. If we're seeing basically the in-spiral of these supermassive black holes as they slowly come together, what LISA is seeing is the actual collision between the supermassive black holes. So it's really completing the entire story. Pulsar timing array experiments will be able to see what's happening to gravity in these gravitational waves as the black holes are in-spiraling over many millions of years. And then LISA will actually see what's happening as these huge, gigantic behemoths of the universe actually collide. So it's going to be a very complementary scientific instrument that will really open up another sort of complete window into our universe, I think.
Because that's one of the big questions. Do they bump into each other or do they simply merge in a very smooth process? Yeah, it's one of the last, there's something called the no-hair theorem, which I think is might be what you're alluding to. And yeah, maybe this will help us solve that just a little bit. It's something that people really are looking out for at the moment. That's Dr. Matt Miles from Swinburne University in Osgrav. And this is SpaceTime. Still to come, NASA conducts the first ever aircraft accident investigation on another world, and later in the science report, researchers have found that a single mutation to the deadly bird flu virus could wind up making human infections far more likely. All that and more still to come on SpaceTime. NASA's created history by undertaking the first ever aircraft accident investigation on another planet. Engineers from NASA's Jet Propulsion Laboratory in Pasadena, California and AeroVironment are conducting a detailed assessment of the Mars Ingenuity helicopter's crash back on January the 18th, 2024. That incident brought Ingenuity's historic mission to an abrupt end. Ingenuity was originally designed as a technology demonstration unit to perform up to 5 experimental test flights in the skies over Jezero Crater over a 30-day period. The tiny tissue box-sized twin-rotor helicopter was the first aircraft to fly on another world. Its test flights were so successful, mission managers at JPL quickly began using Ingenuity as a scout to fly ahead of the Perseverance rover, searching out interesting rock formations and ways to avoid difficult terrain. But that all ended on January the 18th, when the tiny chopper experienced an unusually hard landing. The Accident Investigation Board found that the inability of Ingenuity's navigation system to provide accurate data during the flight likely caused the chain of events that ended the mission. Flight 72 was originally planned as nothing more than a brief vertical hop, designed to assess Ingenuity's flight systems and photograph the area. Data from the flight shows Ingenuity climbing to a height of 12 metres, hovering and then capturing the images. It then initiated its descent at 19 seconds, and by 32 seconds the chopper was back on the surface, but then halted all communications. The following day, mission managers re-established communications with the chopper, and images that came down 6 days after the incident revealed that Ingenuity had in fact sustained serious damage to its rotor blades during its landing. The investigators believe a lack of surface texture gave the navigation system too little information to work on during the landing phase. See, the helicopter's vision navigation system is designed to track visual features on the surface using a downward-looking camera, viewing a well-textured, pebbly but flat terrain. Now, this very limited tracking ability was more than enough for carrying out Ingenuity's initial 5 test flights. But by Flight 72, the helicopter was now in a region of Jezero Crater which was filled with steep, relatively featureless sand ripples. One of the navigation system's main requirements was to provide velocity estimates that would enable the chopper to land within a small envelope of vertical and horizontal velocities. Data sent down during Flight 72 shows that about 20 seconds after takeoff, the chopper's navigation system couldn't find enough surface texture to track. Images taken after the flight indicate these navigation errors created high horizontal velocities at touchdown. In the most likely scenario, a hard impact on the deck caused Ingenuity to pitch and roll. And this rapid attitude change resulted in extreme loads on the fast-spinning rotor blades beyond their design limits, snapping all 4 of them off at their weakest point, about a third of the way from the tip. The damaged blades then caused excessive vibrations in the rotor system, ripping the remainder of one blade from its root and generating an excessive power demand, resulting in the loss of communications. Although Flight 72 permanently grounded Ingenuity, the helicopter still lives, beaming back weather and avionics test data to the Perseverance rover about once a week. That weather information could benefit future missions to the Red Planet, and the avionics data is already proving useful for engineers working on future designs for other aircraft and vehicles for use on Mars. The report's findings are expected in the next few weeks, and they'll benefit future Mars helicopters, as well as other aircraft designed to operate on other worlds, including the Dragonfly mission to the Saturnian moon Titan. NASA's also working on new, more sophisticated Mars helicopters for the planned Mars Sample Return mission with the European Space Agency, that's slated to launch by at least 2030. After almost 4 years of continuous operations on Mars, mission managers have realised that not everything needs to be bigger, heavier and radiation hardened to work in the harsh Martian environment. Inspired by Ingenuity's longevity, NASA engineers have been testing smaller, lighter avionics that could be used in the vehicle designs for the sample return campaign. The data is also helping engineers as they research what a future Mars helicopter could look like and what it could do. A new major helicopter designed for Mars, known as the Mars Chopper Rotorcraft, would be some 20 times larger than Ingenuity, and it could fly several kilograms of scientific equipment, autonomously explore remote Martian locations, and travel up to 3 kilometres a day. That compares to Ingenuity's longest flight, which was 704 metres. As far as NASA are concerned, it looks like drones based on Ingenuity may well be the exploration way of the future. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A lab-based study has found that a single mutation in the deadly H5N1 bird flu virus, which is currently affecting sheep and cattle in the United States, could end up making human infections more likely. H5N1's a strain of flu originally found in birds, but can also infect livestock and humans, although there's been no significant evidence of it spreading between people yet. The researchers made small changes in the lab to a strain that occurs in cows and found that a single mutation makes the virus far more specific to humans. A report in the journal Science warns that potentially it could make it much easier for the virus to infect humans. And in the wake of the gain-of-function research with the COVID SARS virus at the Wuhan Institute of Virology, it's important to note that these new bird flu mutations have not been observed in the wild. A new analysis of the oldest known genomes for early modern humans who lived in Europe around 45,000 years ago suggests that modern Homo sapiens and Neanderthals mixed in a single event far more recently than previous estimates. The findings, reported in both the journals Nature and Science, looked at the genomes of 7 people who lived between 42,000 and 49,000 years ago in Germany and Chechnya. These people were all part of a small, closely related human group that first split off from the population that left Africa around 50,000 years ago and would later go on to settle the rest of the world. Although they separated early, the Neanderthal DNA traces in their DNA shows that the DNA mixing event, common to all people outside Africa, happened around 45 to 49,000 years ago, much later than previously thought. The study also examined DNA data from 275 present-day humans and 59 ancient individuals who look at Neanderthal ancestry in modern humans over the last roughly 50,000 years. It found there was a single shared extended period of gene mixing that likely occurred between 50,500 years ago and 43,500 years ago. Have you ever wondered why journalistic standards are so bad these days? Well, a recent study may have the answer, and it turns out to be far more than just the poor quality woke media courses that are being taught at universities these days. The study, commissioned by the London Press Club, shows that journalists' brains show a lower than average level of executive functioning, meaning they have below average ability to regulate their emotions, suppress their biases, solve complex problems, switch between different tasks, and show creative and flexible thinking. The study looked at 31 journalists who were asked to carry out a series of tests, answer a questionnaire, and report their eating and drinking habits. Researchers found that the journalists' brains were functioning at a subpar level, probably because they were consuming far too much alcohol, caffeine and sugar. But it also found their love for their work helps them fight through these difficult times. Over 40% of participants said that they drank 18 or more units of alcohol per week. The recommended maximum weekly consumption is 14 units. That equates to 1.5 bottles of low-alcohol wine or 4.5 pints of beer a day. Well, British paranormal experts claim that your average ghost has a very limited lifespan, which, when you think about it, it's a bit of a contradiction in terms. Tim Mendham from Australian Skeptics says this so-called expert claims most ghosts lurking around nowadays are less than 100 years old.
It's very sad, isn't it, if you think of all these stately homes in the UK which all have their own ghosts.
Well, every pub in the UK has a ghost just about, doesn't it?
Absolutely. Every pub in the UK is haunted. Always had these little CCTV videos of a glass moving across the counter, etc., or a door opening and closing, or a chair spinning around, and it helps sell people to stay there. There's one theory by a paranormal expert, a guy named Brian Sterling Veet, who's saying that ghosts run out of energy according to the second law of thermodynamics, which means that energy dissipates. So therefore, if a ghost is pure energy, therefore they're dissipating, and they'll only last about 100 years, which doesn't explain ghosts which have been around for hundreds of years. But he said eventually all the ones that are old ones, we're losing track of them. There are not as many sightings as there used to be. So he reckons that 100 years is about it.
For our listeners who want to know the second law of thermodynamics, you can't pass heat from a cooler to a hotter. You can try if you like, but you're far better notter.
There's another guy we spoke about a while ago who reckons the same sort of thing, that goes to running out of puff, running out of energy, and he was suggesting a bit of nuclear power that help boost them. I'm not quite sure how you plug in a ghost to a nuclear power station, but never mind. This paranormal rescue service fellow reckons that this is a major issue, that ghosts are disappearing, that once notably haunted locations are increasingly less frequently haunted, and some haven't been for a long time, which might actually be explained by the fact that people get bored with a particular site and are not that interested, or it's been debunked thoroughly, but that's beside the point.
That's Tim Mendham from Australian Skeptics. that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.